Alright, I want to try to solve this problem. If I can find my pen. There we go. So, in order to solve an equation with fractions, I want to first identify the least common denominator. In this case, it's fairly simple. You could just multiply 4 and 5 to get 20 as our least common denominator. Sometimes it's a little more complicated because there will be a common factor, but we will cross that bridge when we come to it. So now that I've identified this, my preference is to multiply everything by that 20. So I will essentially just rewrite this problem. I'm going to give myself a little more space here. And multiply each of these terms by 20. Okay. Now, you can do some things here to help you out with simplifying this. If it helps, you can write these. Oh, well, this one doesn't really need it. For these terms where you've got a number times a fraction, you can take that 20, you can take that number and write it as a fraction just by writing it over 1. I don't really need to for this next term because 1 is not a fraction, 20 is not a fraction. I can just multiply those straight up. I get 20 times 1 is 20. Now over here, again, same thing. Since I've got a fraction over here, you might want to write this 20 as a fraction, like so. Now from here, you've got two options. Right? So hopefully I'll have room to do both of these. The first option is to just multiply your fractions straight across. So 20 times 3 gives you 60 x, and then 1 times 4 gives you 4. Over here, 20 times 1, again, that's not a fraction, so that's relatively straightforward. It's just 20 times 1 is 20. And then finally, on the right, 20 times 7 is something terrible, 140. And then 1 times 5 is 5. Now, the purpose of this, the reason we multiplied by that 20 in the beginning is the fractions we have will now reduce. I can do 60 divided by 4. And I get, gosh, what is that, 15? I feel like it's 15. 20, there's nothing to do there. Except write it correctly. And then 5 goes into 140 a bunch of times. Let's see, 28. Okay. And now we've got a much simpler linear equation which you could solve as usual. I didn't leave enough room, so I'm just going to sneak in some new paper here and keep on going right below this. So in order to finish solving this, I need to move the 20 over. I can do that by adding 20 to both sides. I get 48 there on the right, and then I can divide by the 15. So the 15 cancels on the left. On the right, 48 divided by 15, it could be some awful decimal. I don't want to write that as a decimal. Very rarely will we use a decimal in this class. Instead, we will look for a way to simplify this by pulling out a common factor. In our case, 48 and 15 are both divisible by 3. So I divide the top by 3, I divide the bottom by 3, and I get, I say that's divisible by 3. 48 divided by 3 is 16. And 15 divided by 3 is 5. So that's how we would leave this problem. All right, an alternate way to do this. So I'll separate this out. An alternate way to do this problem, in a much nicer way I would say, is like so. And I'll write out this first step again. We've got 20 times 3/4 x minus 20 times 1 equals this 20 times 7/5. So what I'm going to do here, as opposed to last time I multiplied the numerator. I multiplied 20 times 3 and I got 60. I multiplied 20 times 7 and I got 140. Now, what I want to talk about here is PEMDAS. Specifically, PEMDAS is not the end-all be-all of the order of operations. In reality, you can do division and multiplication in whichever order you like. You can do division first. Similarly here, I could do subtraction first if I want to. There's nothing that says you have to do the multiplication first each time. And that's going to make this a lot easier, because rather than doing 20 times 3 and getting this large number, 60, I'm going to go ahead and do the division first. Right? I know I'm going to have to divide eventually. I can't divide 3 by 4, but I can divide 20 by 4. And that gives me 5. 5 times this 3x. Here I don't have to do that. 20 times 1 is just 20 again. But over on the right, again, I wanted to do my division first. 20 divided by 5 gives me 4. So much nicer. So now I don't need a calculator. I can do this all, using my times tables. Before, remember, I had to do something like 140 divided by 5. I can't do that in my head. I had to pull up my calculator. But I can do 20 divided by 5 to get 4. I can do that in my head. And hopefully, we should get the same answers here. On the left, 5 times 3x gives me 15x. That looks familiar. Minus 20. On the right, 4 times 7 equals 28. So this looks identical to what we had over here, except I had smaller numbers to work with. I could do it all in my head. So I add 20 to both sides. I get 48 on the right, and I divide by 15. I get x equals 48 over 15. And again, I can simplify that by dividing each of those by 3 and getting 16 over 5. So 2 ways to do this. There are, in fact, a lot more ways than this. We'll stick with 2 for now. But if neither of these mesh with you, you can always talk to me, and I'll show you, a dozen more methods. Okay, next up on our list is solving linear equations that have no solutions or have an infinite number of solutions. So I have 2 examples here. We're asked to solve this. This is an equation. I know I can solve an equation. Well, hopefully, I can solve an equation. In order to do that, I want to get all my variables on one side and number terms on the other. So going through our steps, there's nothing to distribute. I don't have to worry about that. There are no like terms to combine, so I don't have to worry about that. My next step is getting the variables on the same side. And I see I've got a 3x on one side and a 3x on the other, which may warn you that something is a little awry here since we have the same variable term on each side. So I'll start off by subtracting 3x, and then you quickly see that this has gotten a lot scarier. Now, I know I've got a 5 and a 6, but what happens with the 3x? A lot of people want to do strange things here. They'll write 1x, or they'll write out x in some way, shape, or form. Don't do that. 3x minus 3x is 0. There's no more x over here on the left. Same on the right. 3x minus 3x is 0. The x's are just gone. And we're left with this equation, or this statement. 5 equals x. 5 equals 6. And the question is that a true statement? Is that true? Does 5 equal 6? No. 5 doesn't equal 6. So that's a problem. When we look back on our notes, I believe we talked about this already. One of our definitions of a solution to an equation is something that you can plug in to make it equal. Right? That was one of the things, well, one of my classes came up with this week. There are lots of other ways to phrase this. You could say something you can plug in to give you a true statement. Right? So to make it equal, or to make a true statement. Right? Now the question is there anything we could have plugged into our equation here that would make this a true statement? Right? For instance, if I plug in 1 here, you know, I'd have 3 times 1 is 3. Here I plug in 1, I get 3 times 1 is 3. So let me actually write that up. So for an example of this. So I'm just guessing some random solution here. I just want to help you visualize this. What happens? I have 5 plus 3 equals 3 plus 6. You see, I've still got my 5 and my 6 on both sides, and I have this additional 3. You know, I could get rid of that 3 just like we did before. I still get 5 equals 6. It turns out no matter what you plug in for x, this will always happen. You're going to have 3 of them on the left side, 3 of them on the right. Those parts will essentially balance out, and you're still left with this difference of 5 and 6 here. And 5 does not equal 6. So what does that tell me? It tells me that we have no solution here. Right? No matter what I plug in for my x's, those are still going to be balanced on both sides. That part is still going to cancel out on both sides. I'm still going to be left with this final statement that's just not true. Right? Not a balanced equation. So when that happens, when your variables cancel and you're left with something that's not true, well, that just doesn't have a solution. Okay, part B, looking at linear equations with no solution or infinite solutions. Since we just have one with no solution, you can probably guess what's going to happen here, but I'll walk you through it anyway. So you may notice as before, we don't have any parentheses. We don't have to distribute anything. We don't have any like terms to combine, so we move on to getting our variable terms on the same side. So we see we've got a negative 4t on the left and negative 4t on the right. At this point, you may be a little concerned. So we just keep on going with what we know. We want to add 4t to cancel that out. Just unfortunately, I guess the 4t cancels on both sides. So we get really scared. Once again, when your variable terms cancel out, that's fine. Just let it happen. Just let it go. If you love it, if you love something, you gotta let it go. Of course, this t is not coming back to you. This variable is not coming back to you. So I guess that's sad. But anyway, let your variable cancel out. That's fine. And look at what you get. Is this a true statement? Yes, this is a true statement. However you want to phrase that. So this is a true statement. Right? This is a balanced equation, etc. Lots of ways to think about this. So the question is, what happens when I plug in some number for our variable? What happens when I plug in something for t? Is that going to change? Pick any random number you want. I don't know. Let's do something exciting. Let's try t equals 3. And again, this is just for fun. This is not part of the problem. This is to help you understand what's going on here. So I'm just trying randomly 3. So I'm going to have negative 4 times 3 plus 28 equals 28 minus 4 times that 3. So what is going to happen? On the left, I still have my 28. On the right, I still have my 28. It's just that now we have an additional term. Minus 4 times 3 is 12. Or negative 12, I guess. On the right, negative 4 times 3, negative 12. So you see, I've still got my balance, 28 equals 28. I've just subtracted 12 from each side. So you can imagine this like a seesaw. We've got a 28-pound person, a 28-pound person, and we've got a nice balanced seesaw. Now this guy, I don't know, maybe he throws up or something. That's a lot of throw up. Man, I shouldn't make these analogies. I don't know. Maybe they've been seesawing a long time and they've lost a lot of weight. This person has lost 12 pounds. This person has also lost 12 pounds. What happens? It's still balanced, right? In fact, we could add 12 to both sides, right? And we're still going to get 28. We're still going to get this balanced equation. So I know this analogy is a little silly. You don't have to go through this. This is what tells you your answer. You've worked it out and you get a true statement. You've got a balanced equation. That tells you that you have an infinite number of solutions. Anything you plug in for your variable is going to still leave you with this balanced equation, this true statement. So what we write here is that we have infinite solutions. Alternately, we could say that any real number is a solution. There are lots of ways we'll write this over the semester. I don't think we do interval notation, but you may see it. So I'll go ahead and write it. Another way of saying it is your solution is anything from negative infinity to positive infinity. I don't believe that's in this section, but I'll go ahead and throw it in there. But the key idea here is when your variable cancel out and you get a true statement, this has infinite solutions. Anything will work here for your variable. Infinite solutions. All right, in this section, we are asked to evaluate a function. We've been given a function f of x is equal to 2x squared minus x plus 3, and we've been asked to evaluate this at a variety of things here. They're not necessarily just numbers. We've been asked to evaluate this a couple different ways. So the first case, we're asked to evaluate this at negative 7. So what is this negative 7? This is the value we're substituting in for x. And that should be pretty easy to remember, because normally a function is written as f of x. If they're saying f of negative 7, well, they're saying x is negative 7. So everywhere there was an x, now we are replacing that with negative 7. So this is equal to 2 times you see here all I've done is I've replaced the variable with just some parentheses, and now I'm going to fill in that negative 7 that we've been asked to substitute in. So you got to be careful with your order of operations. I see a lot of people messing this up. You have to deal with this the parentheses. Well, there's nothing in the parentheses. Look at there. There's nothing to do in those parentheses. But you've got to do your exponent before you deal with your multiplication. So don't multiply 2 and negative 7. Do your exponent first. So negative 7 squared is 49, a positive 49. So now we've done that exponent. For the other terms, we don't have a lot going on. We'll go ahead and just do what we can. There's nothing to do in this next one except distribute this minus sign. So distributing this minus sign, there's already a minus sign inside of there, so minus times minus, that's a plus. Or minus a negative is plus. And then finally, nothing to do with that 3, so we'll just carry that down. All right. 2 times 49 is 98. We could add all that together. We could have added the 7 and 3 right there. In fact, I really like that idea. I won't do it now. I'll do it here. And you could do this all at once. I just like to do as much as I can in my head. And this is really nice. 7 plus 3 is 10. 10 is pretty easy to add to 98. Right, I add 10 to that, I get 108. Next up on our list, very scary, they've added in another variable. They've added an a here in addition to the number 5. That's okay. We're going to do the exact same thing we did before. Let me separate this. So I have 2 times blank squared minus blank plus 3, and now I'm substituting in 5a. Okay. So what will I do? Same as before, I want to, there's nothing to do in my parentheses, but I need to then move on to my exponent. All right. So 5a squared, that tells me I want to multiply 5 by itself. 5 times 5 is 25. I'm squaring the 5. How's that? So 5 squared is 25. What about a? What happens when you square a? You just get a squared. So 25a squared from squaring 5a. Next, minus a 5a. Nothing to do there, just minus 5a. And then finally, plus 3 again. Okie dokie. I've dealt with my exponent. Now I can deal with multiplication. I can deal with multiplication on my pendulums. So 2 times 25a squared. Well, I'm just multiplying the numbers there. So I get 2 times 25 is 50. I carry down my 5a, and I carry down my 3. So what do we do at this point? We're done. We don't have any like terms, right? We have an a squared term, we have an a term, and we have a constant term, right? We have a term that doesn't have a variable. So none of these are like terms. They have different variables, or their variables are raised to different powers. Part C, probably the scariest one of all. We've been asked to evaluate this at a minus 4. Incidentally, this is called a binomial. Not that anyone cares other than me. Bi for 2, nomial for, I guess, number. We'll say number. Why not? I don't know enough Greek / Latin. Alright, so same as before. I'm going to write out my function. And then just substitute into it what they want. Ooh, I should probably write the square, huh? They want me to substitute in a minus 4. I'm just going to write in an a minus 4. And we will go from there. Now, this is tricky. This is you may want to put a star by this. Lots of people want to mess this up. When you're squaring a binomial like this, when you have 2 separate terms in there, you don't just square the first term and square the second term. What does it mean to take something and multiply by itself? Maybe I should do this up here somewhere. I'll just do it off to the side so I have some room for it. What does this mean? A minus 4 squared. What does it mean to square something? It means to take it and multiply it by itself. Now hopefully seeing it written like this helps you see our next step. When we've got 2 binomials multiplied together, we want to FOIL this, meaning we multiply the first terms together. A times A gives me a squared. And then I want to multiply my outer terms together. A times negative 4 is negative 4a. I want to multiply my inside terms together. So minus 4a. And then finally I want to multiply my last two. So negative 4 times negative 4 is a positive 16. And I can simplify that slightly because I've got two like terms there. I've got a negative 4a and another negative 4a. Together that makes negative 8a. So what I've done is I've now multiplied this out. I'll go ahead and write out what we got from that. We got a squared minus 8a plus 16. And everything else I'm going to carry down. I'm going to carry down my 2. I'm going to carry down my minus a minus 4. And carry down my plus 3. So all I did is I worked this out up here off the side. And now I've taken my simplified version of that and plug that in. Right. So now I've dealt with my square. Right, the square is gone because I did the squaring up here. All right. So now we can distribute. So I want to distribute 2 to each of these. So 2 times a squared is 2a squared. 2 times negative 8 is negative 16a. And then 2 times 16 is this 32. On the right, not on the right, next up, one of my favorite things to drill y'all on, you've got a minus here in front of this. You've got to distribute that minus to both terms. So the positive a becomes a negative a. We had a negative 4. Minus that negative 4 gives you a plus 4. And this poor old 3, we just keep on carrying down. We will carry him down. All right, we've got a bunch of like terms. I don't see any other a squared terms, so I'll go ahead and carry down the 2a squared. But I've got a couple of a terms. We've got a negative 16a and a negative 1a. Together that makes a negative 17a. Then I've got a 32, a 4, and a 3. I can add all those together. 32, 33, 34, 35, 36, 37, and I feel like that is 39. Let me try that again. Okay, yeah, I can't add very well. All right, so that's a wrap on that one. Kind of tedious, but you got to get in the habit of when you see a binomial squared, you've got to form that out. All right, continuing along with evaluating a function. Now we're going to look at part B, using a graph to evaluate a function. This is super easy, and this is essentially free credit on your tests. You know, this will come up throughout the year. And let's see, what do the instructions say? Use the graph to find each of the following function values. Find f of negative 3. They've given you an equation. You know how to do this with the equation, right? If I give you something like this, if I say find f of negative 3, you know that they've given you an x value and you can plug that in. But you don't have to do that, right? Because you know that the x value is negative 3, looking at my graph, my x-axis is this one that goes side to side. I can look at that value. I can look at x equals negative 3. Right, that's right here. Little arrow there. And say, what is my function value? Well, since they've got this graph, even if you had no idea about math, you can probably piece this together if you sat there and stared at it for a minute. When I see x is negative 3, I see that there's some other number associated with that. When x is negative 3, I've got the value on my graph. I've got the y value of the graph is positive 3. And that's actually what we're looking for. When they say find f of negative 3, they're looking for that y value. Okay? And looking at my graph, I can see what y is. When x is negative 3, y is positive 3. That's an important thing that you may have actually seen written at some point in your life. This notation, f of x, just means y. This is another way of writing y. So these are interchangeable. If they ask for what f of negative 3 is, they're saying what y value is that. You'll see often when we're looking at equations, we'll use those interchangeably. So for instance, here they've got f of x equals x squared minus 6. Just as often, you'll see this as y equals x squared minus 6. And that is because f of x just means y. They ask you what f of x is, they're saying what is y. So part B, find f of 1. Well, what is the x value? Again, we know that your x value is whatever's in those parentheses. In our case, that x value is 1. What are we looking for? They want us to find f of 1. They're asking us to find y. Asking us to find the y value when x is 1. So let me look at my graph. Here is where x is 1, right? Here's my x-axis. I just go over to 1. Right, there's 1. And I go down to see what my function value is. So right there, that's where x is 1 on my graph. And what y value is associated with that? It's negative 5. And that's it to these. These are really not too bad. All right, next up, we're doing everyone's favorite part of math, applications, or word problems. Looking at this first example, example 10, I should probably read through this, huh? Let's see, Metro Taxi charges a $2.50 pickup fee and $2 per mile travel. Super. Grayson's cab fare from airport to his hotel is $32.50. How many miles did he travel in the cab? Got it. So we've got some numbers here. Let's see, $2.50, and that's a pickup fee, and we've got $2 per mile. All right. Then we've got this guy Grayson. His cab fare from the airport to his hotel is $32.50. How many miles did he travel? Okay, so I've got some things jumping out at me from the get-go. I've got these first two numbers that are telling me what this company charges. There are some things to look for here. When I see per, that clues me into this can be the variable. This can be where my variable is going to go. Not always, and in fact, do I have one? Yeah. We'll have plenty of problems if this does not work. But I will say that when I see this $2 per mile, that clues me in that this thing is going to, this cost is going to vary based on the number of miles. That's really nice because they tell me, they're asking for how many miles did this guy travel, and I've got this thing varying based on the number of miles. What does this word vary make you think of? This is your variable. This is going to change. We can set up an equation now with that as our variable. If we solve for the variable, that will give us our final answer. Whatever we get here, whatever x we get, will be our answer. X equals 10, then how many miles will we travel? Well, that would be 10 miles. All right, other stuff. Metro Taxi charges a $2.50 pickup fee. This is a constant, like a flat rate. And we'll look at a lot of problems like this. You'll get plenty of practice. We look at lots of things where there's just like a fixed cost up front. You know, for example, your cell phone plan might be $40 per month plus $10 per gig of data. So you would have a constant plus a variable cost. So then what does this Grayson's cab fare consist of? That's going to consist of both those, right? It's going to have the constant and the variable cost involved. So let's try to write up an equation here. We've got this $2.50 that you're going to get charged no matter what, and then we've got plus $2 per mile. So the way I'm going to write that is 2 times x. I didn't need all those decimals. It's just, since we're working with money, I try to write 2 decimals, right? because that's how money works. We have two decimal places. So once we take this flat rate and add it to his $2 per mile, right, where X is the number of miles, that should give us his total fare, $32.50. So if he goes 1 mile, we have 2 times 1, he's going to get an additional $2. If he goes 2 miles, that's 2 times 2, to give us $4 extra. If he goes 3 miles, that's 2 times 3, that would be an additional $6, etc. And if we were less sophisticated, if we were early mathematicians, that's how we would do this, is trial and error. But through the miracle of algebra, we can now solve this. If I subtract that 250, 3250 minus 250 is 30. And again, you could get away without all of these decimal places. I see a lot of students who make rounding errors when it comes to money. It'll say, what's the nearest cent? You need to round that to the second decimal place. That's why I try to use the decimal places, the 2 decimal places when we're dealing with money. All right, so I've got $2 times X equals $30. I can now divide by that. $2. And you could punch that all in your calculator. Although you've just got 30 divided by 2, which gives you 15. So there you go. Rather than just guessing randomly, we could actually work this out and avoid a lot of tedious trial and error. You may think, I know students are always telling me, well, why not? Actually, no one actually tells me this. But you may ask yourself, why would you do this when you could just do trial and error? This is a very simple problem we've given you, or we've given you a problem with very small numbers, where it's simple to do this by trial and error. I could very easily give you a problem where trial and error is not going to get you anywhere. Just by making a significantly higher number, you're going to have a harder time guessing that. Okay, next up, we're looking at a word problem involving a rectangular solar panel. So as soon as I see that, I'm going to draw out a rectangle. They've given me a lot of information there. And if they're talking about a shape, draw out your shape. So this says the length of a rectangular solar panel is 13.6 inches less than twice the width. Whoa, that sounds scary. And the perimeter is 207.4. Find the length and the width of the panel. Well, that is just terrifying. So, 13.6 inches less than twice the width. So what I see here is the length being compared to the width. And when I see twice the width, I'm immediately thinking in my head 2 times W. So, and you don't have to do it this way, but that just jumps out as me as an easy way to write it. Twice the width, 2W. That tells me I probably want to use W as my variable. All right. So if this thing has a width of W, I can go ahead and label those 2 sides as just W, and then I can work on the length. They say the length is 13.6 inches less than twice the width. So I've got the twice the width part, and if I have got 13.6 inches less than that, that means I'm taking that and subtracting 13.6 inches. So this is kind of an annoying way of writing it, but it's one that people actually use in the real world, so that's life. If I've got 13.6 inches less than something, that means I'm taking away this 13.6 inches. So now we've got this length, and since it's a rectangle, this length is the same, 2W minus 13.6. So now we've got our picture all drawn out. We've got our width is just W, and our length is 2W minus 13.6. What other information did they give us? They said the perimeter is 207.4. I know that the perimeter means sum of the sides. They've told me the perimeter is 207.4. So on the other side, I'm just going to sum up all these sides. I've got W plus another W plus 2W minus 13.6 and another 2W minus 13.6. So I've got some like terms to combine. 1, 2, 3, 4, 5, 6. I've got a bunch of W's. 1, 2, 3, 4, 5, 6. And I've got my two constant terms, negative 13.6 and a negative 13.6. Together that makes a negative 27.2. I feel like that's right. Close enough, right? Yeah, that's good. On the left, I carried on my 207.4, and I've got a pretty simple equation to solve, right? I want to move over 27.2 by adding that. And what is this going to be? 2, 3, 4.6. That seems right. 27.34. Yeah. And on the right, the 27.2 canceled, and I'm left with 6W. So finally, I am just dividing. Boy, I hope this works out nicely. I will definitely need a calculator for this. Unfortunately, it did not work out to be a nice, pretty whole number, but that's okay. We can still do this. So the question was, find the length and the width. We found the width. What was the length? It was 2W minus 13.6. So 2 times that width we just found, 39.1 minus 13.6. And I'm just going to do all this in my calculator because I'm feeling super lazy. Two times 39.1 minus 13.6 gives me my length is 64.6. And we've done it. All right, our last example. Money is borrowed at 18% simple interest. After 1 year, $750.48 pays off the loan. How much was originally borrowed? Whew, that's a lot to unpack. So some things you're going to want to know about how interest is calculated. Interest is equal to principal times rate times time. Principal is a word that we're going to use a lot in here. Anytime we're dealing with money, this will probably come up. Principal? I feel like that's how you spell it. Principal is just the amount you invested or the amount that you borrowed. It's just the initial amount. So if you do any kind of business or accounting courses, that's a term you'll get really familiar with. This is a common banking type term. So that's going to be kind of important here. So other stuff you need to know. When you pay off a loan, you pay off the interest, right? But you also pay off that initial principal. You're going to have to pay off both of those. So keep that in mind. You're going to need to pay off the not only the interest we're going to calculate using this formula, but also the principal itself. That's very convenient. They asked us how much was originally borrowed. They're asking us for P. Okay, so let's write out an equation based off of what we've come up with. So like the payoff amount is going to be equal to the principal plus the interest. And we just said we've got a formula for the interest. Interest was principal times rate times time. This is very convenient because we've got some repetition in variables. We've eliminated one. We've eliminated this I variable. This is really nice because we know the interest rate, we know the time. When we plug those in, we've got just the one variable left. So let's go ahead and do that. How much did they say paid off the loan? They say $750. To that, we still don't know P, but we do know the interest rate was 18%. So in case you haven't seen it before, you're about to. When we're working with percentages here in our accounting type questions, we're always going to write these as a decimal. In fact, basically anytime we're working in percents in this class, we're going to write them as a decimal. So to do that, you just move your decimal 2 places to the left. So 18% becomes 0.18. If it had been, I don't know how far off tangent I'm going to get. If it was something like 5%, we would move that decimal place over 1, 2. Well, that's confusing. In order to do that, we would have to add in a 0 in front of that 5. So that would be like a 0.05. So when we've got 2 digits, it's really easy. You just move it over in front of that first digit. If you don't have 2 digits, you're just going to have to add in a 0. So not related to this problem, but might as well tell you now. All right, finally, how much time? Time is 1 year. So 1. And that's pretty common. I think all the ones we give you, I'm almost positive they're all going to be just 1 year. So that should make this really convenient for you. So what do we have? I want to rearrange this slightly and simplify it. I didn't do anything in the first part. But over here, 0.18 times 1 is 0.18. And I also want to write that in front of my variable, just because that's common practice to write the number in front of the variable. Lastly, I want to write in the coefficient in front of this p. What number goes in front of p? What number goes in front of the variable if there isn't one? Hopefully you're shouting at your screen that it's 1. You know, when you don't have a coefficient, your coefficient is an understood 1. And now you've got something you can add to that 0.18. You've got like terms here, right? They both have a p in them. You know, you've done this before with x's. P is just another variable, right? You can work with it just like you work with x, and you can add those coefficients together. So 1 plus 0.18 is 1.18p. Very nice, because now we can divide that to get p by itself, which is always our favorite thing to do with a variable, is get it by itself. Bust out the handy-dandy calculator, because there's no way I'm doing that by hand. And nobody got time for that. Okay, 750.48 divided by 1.18, I get 636. Well, that's a nice round number. So the question as to how much was originally borrowed, we have a solution, $636. You should do a quick gut check with these problems if you can. How much was originally borrowed? $636. Does that make sense? At the end of the year, $750 pays off the loan. So, if nothing else, you should say, okay, the principal's just a little bit less than what you pay off. And that makes sense, right? Because you're going to have to take this $636 and pay some interest on that, right? So you should have, your payoff amount should be slightly larger than our initial amount, our principal. You'll see similar types of problems to this, where you're setting up an equation like this. We do this with tax a lot. You know, if you have so I'll go ahead and write out this equation just for funsies. Like if you have the total cost of something, when we're talking about tax, you would pay like the item cost plus the tax on that item. But how do you calculate the tax on something you're buying? It's the tax rate times the however much the item cost. So if I carry down this stuff, you see that this is the same type of situation where we've got a repeat here. We've got the item cost over here, right? And you've got the item cost over here. Because when you're buying something, you're paying for that cost, and tax is calculated by multiplying the rate by that cost. So you see, once again, we've got the same thing here. We've got two terms with the same variable. That will be very commonly be a variable. So it would work out just like this one. So just a heads up, in case you encounter a problem like that, this is just a common technique for certain types of problems involving money.